All right, question 1 for the work, energy, and power unit. So a friend's car is stuck in the ice, and you push down on the car to provide more friction by way of increasing force normal. This allows the car's tires to propel it forward 5 meters onto less slippery ground. How much work do you do? Well, if we look at the vehicle and we look at the force applied, in other words, the force that you provided downward on the vehicle, and we look at the direction of the movement of that vehicle, you can see that our angle here is 90 degrees. Well, cosine of 90 degrees is 0. Therefore, no work was done in this case. Question 2. You push a crate up a ramp with a force of 10 newtons. Despite your pushing, the crate slides down the ramp 4 meters. How much work do you do? Well, as you can see, we have our force and we also have our displacement. That means we can look at a schematic diagram to help conceptualize the problem. So the force is applied up and parallel to the ramp. However, the displacement is down and parallel to the ramp. So when we look at using the work equation here, we're going to use the magnitude of the force, the magnitude of the displacement, and the cosine theta will basically tell us if it is positive or negative work. However, throughout this series of questions, I'm going to implore you to just kind of reason through it on your own. If we have a force up in parallel, yet the displacement is down in parallel, i.e. opposite the direction of the force, then we're going to have negative work. However, placing this into our work equation, cosine of 180 degrees is -1. Therefore, we learn that the work done in this problem was -40 joules or -40 Newton meters. Question 3. How much work is done by lifting an 8-kilogram box from the floor to the height of 2 meters above the floor? Well, again, let's start with a schematic. Heck, let's even throw in a free body diagram to help us conceptualize the problem. So here we have a crate on the floor. We're going to apply a force that's an upward force, okay? The displacement of the object is also upward. So when we look at using our work equation, we can see that we're going to end up with something that we've seen in the last unit repeatedly, where if we sum the forces vertically, we learn that the force applied is equal to the weight of the object. Now, there is an assumption that's being made here, and that assumption is that this is occurring at a constant speed. In other words, there is no acceleration. That allows us to say acceleration vertically is 0. Therefore, force applied is equal to mass gravity or the weight of the object. Then we can use our work equation and plug in our values, understanding that 8 kilograms times the acceleration due to gravity gives us 80 newtons. The displacement upward is 2 meters, and we're going to get a cosine 0. Or, as I've just said, you can simply say to yourself, okay, the force is upward, the displacement is upward, this is positive work, and indeed the answer to this question is 160 joules. In question 4, a 15-kilogram crate is moved along a horizontal floor by a warehouse worker who is pulling on it with a rope that makes a 30-degree angle from the horizontal. Sounds like we're going to need some trigonometry here. The tension in the rope is 69 newtons. The crate slides a distance of 10 meters. How much work is done on the crate by the worker. Let's draw a schematic diagram to help us understand this problem. So we have the mass of the object, we have our tension force. That tension force is 30 degrees above the horizontal. So I have resolved the tension force into the horizontal and vertical directions. I've also made note here that the change in position is 10 meters. So that's going to help us to figure out the work done by the person on the rope, okay, or on the crate rather. So what we need to look at is the component of the force that is parallel to the direction. That's all we need. So if we look at this, we can go through the motions here that the force is equal, or excuse me, work is equal to force displacement cosine theta. All right, and cosine theta is equal to the horizontal component of the force divided by 69 newtons. That's the trig. Therefore, 69 Newton cosine 30, or theta, which is 30, is going to give us that component. So again, guys, look, this is the only component doing work, okay, that for the warehouse worker. It's that force, in this case, that component of the force parallel to the direction of the displacement of the object. All right, so after the last unit, you can probably go through and just say, oh, okay, that's the adjacent side. That's the hypotenuse, 69, cosine theta, in this case, 30. All right, so that gives us the force component we need. Then we can take that and simply plug it into our work equation because we've now identified the component of force actually doing the work. Okay, now because we found the component that's parallel and in the same direction, that's cosine 0, which is 1, as far as this theta is concerned. Okay, and so again, just so you don't confuse it, this is the horizontal component of the force of tension, and we're multiplying it by the distance, the magnitude of the displacement, and we're getting around 598 joules, 600 joules, somewhere in there. Okay, now if we also look at this here, we have 69 newtons multiplied by 10 meters, cosine 30. This will also give us the same answer. So what you want to do is really try to, let me go ahead and, so here we have the resultant vector, the hypotenuse, and for the work equation, we want the angle between the actual force applied and the displacement, which in this case is parallel and horizontal to the ground. So 69 times 10 cosine 30 would give you the exact same answer. My point in doing this is I want you to use whichever is the most intuitive to you. If you are a hardcore sum the forces, I see this x component, I'm going to go ahead and go through and isolate that and then multiply it by the distance, acknowledging that the angle cosine 0 is 1. Great, you get the same answer. If you are able to look at this and say 69, which is the hypotenuse or resultant vector, the overall force of tension, times 10, cosine theta is going to give us the same answer, 30 for theta, then that's also great. My point again is choose whichever one is most intuitive to you. A word of caution here. If you get into a plug and chug mode with this formula, you can run into some trouble. So I would urge you to always really think about the components and which components are actually doing work, as opposed to blindly plugging into the work equation. And in this case, yes, the answer is the same. Question 5. In the previous question, assume the coefficient of kinetic friction between the crate and floor is 0.4. How much work is done by normal force? How much work is done by the force of friction? Here's our schematic once again, except this time we have a force of kinetic friction. All right, and we also are given the value for the coefficient of kinetic friction equal to 0.4. And we're being asked how much work is done by force normal. Well, if we sum the forces vertically, we're going to find out here that we end up with force normal being equal to mass gravity minus the force of tension vertically, and that's going to be equal to mass gravity minus T sine 30. That's the trig that'll isolate that vertical component. However, there is zero work being done because the angle between force normal and the displacement of the crate is 90 degrees, and cosine 90 is 0. Therefore, the work done is 0 joules. Now, again, you're going to see this, and I will not explain this in detail like I am in these early problems. I just want to give you a rundown of the forces and why zero work is done in this case. Now, let's go ahead and direct our attention to part B, where we can now look at the force of friction and the work being done there. Now, you should be able to say, well, it's opposite direction. That's cosine 180. That's -1. This is negative work. Indeed, it is. Let us sum the forces horizontally and use the physics is fun equation to go ahead and find the overall force of kinetic friction. We have our value from the vertical summation, which comes into play because we do have looking at force normal, we have another force acting vertically and upward, and that would be the force of tension that's acting upwards. So our force normal is not simply the weight of the crate. It is the weight of the crate minus the vertical component of the force of tension, or 69 sine 30. Okay? So that's going to give us our force of kinetic friction at 46.2 newtons. Now we're ready to plug it into the work formula, and we see that the work is equal to 46.2 newtons multiplied by that distance the crate is moved. The theta is 180, which is -1, or you can just reason through it. That's what I'm saying. Just think about it. It's in the opposite direction. This is negative work. But if you want to plug into this formula, you're going to plug in 180. That'll give you -462 joules. All right, question 6. Examine the force versus displacement graph for a block being pulled across a horizontal table. Determine the amount of work done on the book. Okay, so when you're given a force distance graph, you're going to think, what does the area under give me? Well, the area under a force displacement graph, let's look at the units here. If you multiply the force, you get newtons, and distance, meter. That's a newton meter. Heck, that's a joule. That means the area under this graph gives us the work that is being done. So looking here at a rectangle and a triangle, you're going to have a final answer of 27 Newton meters, or 27 joules of work is being done. And because the the force and the displacement are both in the same direction, this is positive work that's being done. 27 joules, final answer. Question 7. A student pulls a 2-kilogram backpack across the ice, frictionless, applying a force of 30 at a 30-degree angle above the horizontal. The velocity as a function of time graph for this motion is shown below. Perform careful analysis and determine the magnitude of the applied force. Then we're going to determine the work done by the student on the backpack. All right, velocity as a function of time. What are we going to do with these graphs? We're going to find the slope, or we're going to find the area under. In this case, the slope will give me the acceleration, and the area under will give me the change in position or displacement. I also have a schematic of this situation showing the force applied at a 30-degree angle above the horizontal. So, first things first, let's go ahead and calculate the acceleration. The acceleration being the slope, which is 0.125 meters per second. Now that we have the acceleration of the backpack, we can then look at summing our forces. You know I love summing forces, so summing the forces oftentimes will help you avoid a careless mistake. So vertically, we have force normal plus that vertical component, force applied in the y direction, minus the weight of this backpack, and there is no net external force and therefore no acceleration. So force normal plus force applied vertically is equal to the weight. Good to know. Always fun to do this. Forces horizontally. We have one force. That is the horizontal component of the force applied. And that is equal to mass times the acceleration horizontally. Well, we just used this motion time graph to find the acceleration horizontally at 0.125 meters per second. Therefore, when we pop in the trig, you can see the force applied, and that's that adjacent side. Okay, so this adjacent side here, which is why I'm using a cosine function here of 30 degrees, is equal to the mass of the backpack multiplied by the acceleration we found from the graph. And so we're able to get the force applied cosine 30 is equal to 0.25 Newton. Okay, so what does this mean? Foremost, this is the direction that's doing the work. And the direction of the force of 0.25 newtons and the direction of the displacement of this object are the same. They are parallel. This is positive work that's being done here. So we have actually isolated that component that's doing work. All right, so we need to find the change in position. Well, guess what? Look at the graph. Find the area under. That is the change in displacement, or excuse me, the change in position or displacement. So we have that information. It's the triangle that we're going to use. A change in position is 16 meters. So now we can use the work equation and take 0.25 newtons multiplied by that distance. Remember, we want the magnitude of the displacement, and we get 4 joules of work that is done. That's a positive 4 joules of work that is done. Okay. Question 8, a box slides down an incline at a 37 degree above the horizontal. The mass of the block, m, is 35, coefficient of kinetic friction, 0.3, length of the ramp, 8 meters. How much work is done by gravity? How much work is done by force normal? How much work is done by friction? What is the total or net work done? This looks like fun. All right, so looking at this object on an incline, recall from our studies of dynamics, look at the geometry here, recall force of gravity perpendicular and the force of gravity parallel, and how those are resolved, and that our angle of the incline is equal to this angle right here. Just wanted to revisit that. All right, so what do we have going on here? We have force of kinetic friction. The block is sliding down, so friction is opposing that, so it's up and parallel to the incline. Force normal is perpendicular to the surface, and then we have our force gravity parallel, which is parallel and down the incline. Okay, how much work is done by gravity? All right, so let's look at what we know. Get a plan for this multi-part problem here. The work done by gravity. Well, there is no work being done by the perpendicular component because the box is sliding down and parallel. Okay, so that's at a 90-degree cosine 90, 0. However, there is work being done by the parallel component. I'm going to show you two ways to do part A. First, I'm going to show you this way, and at the end of the problem, I'll show you another way. And as I've said, whatever way works for you works for me. Okay, so here we go. Force of gravity parallel. Well, throw in the trig. We know mg sine theta, or 37, is that parallel component. So we can simply acknowledge that we understand how to use this formula rather than just plug and chug. Isolate that component that's doing positive work down and parallel, the same direction as the displacement, and we can get our final answer here. 350 newtons sine 37 times 8 gives me 1,685 joules or Newton meters. Now remember, I'm going to show you another way to do this at the end of the problem here. Part B, let's look at what's done force normal. We already went through that intuition. Summing the forces, why not? We know there's no net external force acting perpendicular to the object, therefore that equals 0. And we can also now look at force normal is equal in magnitude, opposite in direction to the force of gravity perpendicular, which is mg cosine theta. And when we look at the work formula and we just plug and chug with this bad boy, we get our 280 newtons multiplied by 8 meters cosine 90, and in the end, it doesn't matter because the answer is 0, okay? That angle is 90 cosine 90, 0, so we just can either approach it like we did at the beginning of the problem and automatically know that there's 0 work done in B, or you can use the mathematics here to put that in and prove it, okay? All right, and now we're going to look at part C. Part C is saying how much work is done by friction. It's going to be negative work because it's up in parallel. It's opposite the direction of the displacement. Physics is fun. Since the box is sliding, we're going to use the coefficient of kinetic friction, 0.3. We're then going to use our summation perpendicularly to find what force normal is, mg cosine theta, and we're going to multiply mg cosine theta by the coefficient of kinetic friction, and we're going to get an answer that the force of kinetic friction is 84 newtons. Therefore, when we plug that in to the work formula, we end up getting the force, which is 84 newtons multiplied by 8 meters cosine 180. Okay, so with that information there, we can come to the conclusion that the work done by the force of friction is negative 672 joules, and that's angle of cosine 180, which is -1, or we just say it's in the opposite direction. Whichever one you're good with, I'm good with. Now let me show you another way to approach part A here. Let's look at another way to approach part A. So, looking at A, we have here, oh, I'm sorry, I need to hit D first. So, the net work, we're just adding up all the work done. The total work, we're adding all the work done. So, the total work to start with was 1685 joules. We found that out. That was the answer to part A, how much work was being done by gravity. There was negative work being done by the force of friction. We're going to subtract that out. So our net work or total work, 1,013 joules. Now let me show you another way to answer part A. Okay, so you can look at our definition for work. And because part A is asking for the work done by the force of gravity, you could also look at the overall force of gravity, and you want the angle between that force and the displacement. That's this angle here, which is 90 minus 37 or 53 degrees. Okay? And if you use that, you can go straight into the work formula and say that work is equal to 350 newtons cosine 53 degrees. Okay? So I want you to use whichever, and of course multiplied by 8. Times 8. And you're going to get the same exact answer as we did how I showed you in part A, where we actually resolved the parallel component. Whichever way you see, whichever way is most intuitive to you, I want you to use that way, please. Question 9. A person pushes a cart to the right with a force. All right, force YC, U on the cart, of 8 newtons at an angle of 40, as shown in the diagram. The cart moves a horizontal distance of 10 meters. What is the work done by the person on the cart? Let's start with that one. Let's take our schematic here and resolve our force, which is the hypotenuse here, into its x and y components. Let's look at our angles here. We're given theta is equal to 40. And we know the displacement is 10 meters to the right. So in part A of this problem, we're going to be looking at the what is the work done by the force of gravity. All right. So we need to think what is happening here with the force of gravity. All right. So again, looking at this scenario, we have 8 newtons sine 40. Okay. That's sine 40. And I guess I jumped ahead. Part A is what is the work done by the person on the cart. Okay, so the person is pushing the cart. So this is the only component that is actually doing work because it is parallel to the displacement. So this is what we are interested in the most. Okay, really that's all we're interested in. So 8 newtons sine 40 opposite gives us this horizontal component, and we multiply that by the distance of 10 meters to get an answer of 51.4 joules. 51.4 joules is the work done by the person on the cart. There's no other work occurring that is parallel to the direction. It is positive work, no other trig needed because cosine 0 is 1. Now, in the next question, what is the work being done by force normal? All right, well, we know force normal. If we sum the forces vertically, force normal minus the 8 cosine 40. All right, so 8 cosine 40 is saying this downward piece here minus mass gravity. So if we did a free body, we have 2 forces acting downward. All right, the force applied, that component, the force of gravity, and then we also have a force acting upward, and that would be force normal, the force of interest in this problem, which by now you're probably saying, Mr. Pedersen, why are you going into so much detail? Because I want you to really understand these problems. Force normal is at a 90-degree angle to the displacement, and cosine 90 is 0. Therefore, work done is 0 joules. All right. Work done by the force of gravity. Okay? Well, it's the same thing. So the work done by the force of gravity, once again, is at a 90-degree angle to the displacement, and thus 0 joules of work is done by the force of gravity on the cart. Okay, part B. Part B, we're being asked if the cart is moving at a constant velocity. Determine the work done by the force of friction. So now we're being told there's a frictional force. So we need to look at the components acting horizontally, and now there are 2 of them. There's the force applied horizontally on the cart to the right that we can find using a sine 40, okay, the one circled in red here. Now we're subtracting the force of kinetic friction, but we're being told the acceleration horizontally is 0. Therefore, through a summation of the forces horizontally, we arrive at the conclusion that the force applied horizontally is equal in magnitude, opposite in direction, to the force of kinetic friction. So you can make some conclusions from that information alone if you conceptualize the fact that the work done by friction is opposite the direction of u on the cart. That's a cosine 180, -1. But if we were to go through and plug in that information, we get the force of kinetic friction must be 5.14 newtons, and therefore the work of kinetic friction on the cart is the force, 5.14 newtons, multiplied by that distance, the magnitude of the displacement, 10 meters, cosine 180, and we learn that it is -51.4. No surprise there if we're saying these are equal in magnitude, opposite in direction as far as the force, because obviously work does not have a direction, but the forces were equal but opposite, and the displacement or distance the same. Therefore, no surprise here. -51.4 joules of work. All right. Part C, calculate the net force on the cart, or the total work, on the cart, or the net work on the cart. So we have the work of the person on the cart minus the work of the kinetic friction on the cart, and therefore 51.4 minus 51.4 is 0. There's 0 joules of work done on this cart. When you include the force of friction and the fact that this cart was moving with a constant velocity, there's 0 work done overall. Question 10. A spring exerts a force as shown in the graph below. How much work is done as the spring stretches from 20 to 40 centimeters? All right, we're probably going to want to get that into our base SI units of meters and bump the decimal 2 to the left. We also have a force as a function of the position, again, units of that position being centimeters. So what are we going to do with this graph? Well, a couple things, really. We can find the slope, which will give us some good information. We can find the area under that displacement from 20 to 40, and that'll give us the work done. We are being asked about the work done, so let's find the area under. Let's look at a triangle and a rectangle and add those up. Again, you can see the units here when we multiply force. Remember, class, force of a Newton is a derived unit. It's kilograms multiplied by meters per second squared. And when we multiply that by meters, we're going to end up with a Newton meter, which is a joule. Sometimes it's good to revisit that. And you'll see me do that throughout these videos where I'll look at units, and I strongly encourage you to do the same thing here. So let's find our work. We have our triangle, plus we have our rectangle, and that's going to give us 20 Newton meters, or excuse me, 12 Newton meters, or 12 joules of work was done as the spring stretched from 20 to 40 centimeters. Again, notice how centimeters were changed into meters because the Newton is a derived unit based on meters. Question 11, we have 8 carts here that are moving along horizontal roads. We have the masses of these in megagrams. All of the carts are the same size, the same shape. They're carrying loads that differ in mass. They're going to be stopped, and they're going to be stopped in the same distance. Rank these from greatest to least on the basis of the strength of the forces needed to stop. This question is really a basic application of Newton's second law, all right, because of the information that we're given here. If they stop in the same distance, then the change in time is the same. So again, this is a very straightforward. Let's go ahead and look at finding the acceleration because we are given the mass. Because we have mass and because we have information that will enable us to find the acceleration, we can find the net force acting on each of these 8 cars. So you can go through the motions, pause the video, look at these, but I have them all figured out, the acceleration, then multiplied by the grams, and you can simply look at these numbers here to get your ranking. So ostensibly, there's work applications here. However, the ranking here, because you're asked on the strength of the forces, this is a good looping question to help us keep in touch with dynamics and forces. This is the best approach. So moving on. Ranking, you can see based on these values, you'll get this ranking from C all the way to the least strength of force being A. Question 12. A spring with a spring constant of 4 newtons per meter is compressed by a force of 1.2 newtons. What is the total elastic potential energy stored in the compressed spring? This is an introductory problem here where we are going to be using the spring potential energy of 1/2 kx squared. This is a plug and chug problem, but it's our first go at solving this kind of problem. Now, what's cool about this problem is you're given some information here. You're given the force and you're given K, and you can use that information to find the how far it's compressed, its change in distance, okay? So looking at Hooke's law, just to revisit what was laid out in the problem set facts, this negative sign, remember that this is a restoring force. So if a spring is compressed one way to the right, let's say, then its restoring will be to the left and vice versa. So that's where the negative sign comes from for the force of a spring and Hooke's law. Now, let's use this information here and go ahead and solve For that distance that the spring was compressed, using Hooke's law, we get 0.3 meters. Now we can move forward and find the elastic potential energy, the energy stored in the spring, 1/2 kx squared. We have everything we need to calculate 0.18 joules. Question 13. The diagram below represents a 155 Newton box on a ramp. There's an applied force that's causing the box to slide from A to B. What is the total amount of gravitational potential energy gained by the box? This is a straightforward application of gravitational potential energy. We're going to need to basically find the height of this ramp, and we can do so using trigonometry. I mean, we have all three sides here, so we can definitely determine that. We have the weight of the box, and we have a force. So you're given what you need. We know that the the gravitational potential energy is equal to mass multiplied by the acceleration due to gravity, multiplied by that height, the change in height. And so we can plug in our information. Where did 15.5 kilograms come from? That's 155 newtons divided by the acceleration due to gravity. Or you could simply just say, hey, 155 times 1.8 meters for the height, and it's the same thing. In question 14, a tennis ball, you're given the mass, is hit straight upward with an initial speed of 50 meters per second. Whoa! How high will it go if we neglect air resistance? Hey, this looks like fun because you're being told to solve using work energy theorem and then go back and revisit some kinematics and UAM. So we have kinetic energy being set equal to gravitational potential energy. All right, we're being asked how high. So look at the initial mechanical energies here. What do we have? Well, this problem starts after the ball is hit. So it is moving very fast. So it has initially kinetic energy. If we set our zero line to be the tennis racket, it has 0 gravitational potential energy. We can then solve for the height of the tennis ball by setting kinetic energy equal to gravitational potential energy and solving for h. So here we have 1/2 mv squared, and we're setting that equal to mg delta h. We have everything we need, and the height 125 meters. Oh my goodness, that is really high. So think about how high that is. That's incredible. But that is the answer to this problem. Okay, so now let's use UAM just to make sure, because we can and because physics is so much fun. So using UAM equations, we can, simply acknowledge, hey, we do not have time. So which UAM does not include time? And let's use that one. And it works out quite well for us. So the final velocity of the ball at the top of its trajectory is 0. And we have its initial velocity, so v naught squared, 50 meters per second squared, acceleration due to gravity. And in this case, solving for the height, or the the vertical distance, y, we get 125 meters, which is still pretty darn incredible if you think about it. Question 15, now let's go back to question 8, where we had a box sliding down an incline. It starts from rest at the top. What is its speed when it reaches the bottom? The purpose of this is to show you how work energy theorem can be much easier than a dynamics or a kinematics approach, like a pure summation of forces. But let's look at our free body diagrams, because that's good for us to revisit this. These will never go away throughout the course. And then let's go ahead and sum the forces, because it's so much fun. So summing parallel, we end up with the following. And when we put in our trig, we have our parallel component of gravity, mg sine theta. We have the force of kinetic friction opposing this motion up in parallel to the ramp. So we subtract that. Where did mu mg cosine theta come from? You know exactly where. Physics is fun. And then we set that equal to mass acceleration parallel. Next, we look at the perpendicular components, and we find that force normal is equal in magnitude to the force of gravity perpendicular. Therefore, force normal equals mg cosine theta. Now let's find the height. We have the distance of the incline, which is the hypotenuse of the triangle. So let's go ahead and find the height using sine, because we want to find height, which is over here. All right, so height would be opposite of this angle. So let's go ahead and do 8 meters sine 37 to get a height of 4.81 meters. Now what we can do is look at the mechanical energy involved here. And so we have the gravitational potential energy is equal to the energy of motion, the kinetic energy, because it is sliding down the incline. But we have an opposing force, and therefore we have negative work being done on this object. And so, as I've mentioned in class, this is the way I set up the problems, but just think about it, guys. Friction's slowing the box down. The box is moving down in parallel to the incline. The force of gravity parallel is down in parallel to the incline. The force of kinetic friction, however, is up in parallel to the incline. So that is negative work. So we're going to end up subtracting that out. Let's look at what this looks like. So mass gravity delta H, which is the gravitational potential energy, equals the kinetic energy plus the work done by a non-conservative force. Subtracting the work done by the non-conservative force from both sides to isolate ultimately the velocity or speed, we then come to the conclusion that our total energy, recall, is 1,685 joules, and now we're subtracting that frictional force multiplied by the distance, which is 672 joules, and we're saying that's equal to the kinetic energy. Algebraically rearranging and solving for the velocity, we get that the box is sliding down with a speed of 7.6 meters per second. Now, there are other ways to solve this problem. This is the easiest. Question 16. A pool Q striking a stationary billiard ball, we're given the mass, gives the ball a speed of 2 meters per second. The average force of the Q on the ball is 200 newtons. Over what distance did the force act? Okay, let's look at what information we have here. We have V naught, we have mass. So if we have mass and initial velocity, we can find kinetic energy the instant after the ball is struck. So we can look at our total energy in this system equal to the kinetic energy final. And we can determine that 1/2 mv squared is equal to half a joule, 0.5 joules. So 0.5 joules of work was done. Where are we going with this? Well, we're asked to find this distance here. We have what we need to actually find the work, and work is equal to change in kinetic energy, which means we can set 0.5 joules equal to the force multiplied by the distance. Again, class, work is equal to the change in kinetic energy. Now, there was no kinetic energy for the ball in the beginning. It was stationary. However, there was a tremendous amount of kinetic energy, or a lot of kinetic energy, relatively speaking, after it was struck. So we can set force distance equal to the energy and solve for x. And in this case here, we get a very small value. So you need to ask yourself, does this make sense? Sure, if you've ever played pool, it should make sense. There's a very, very small amount of distance that the force would act on the ball, okay? So if we wanted to convert this about a quarter of a centimeter would be that distance, and this number is reasonable. It's very reasonable given the fact that it would occur over a tiny distance. Question 17. A ball of mass 2 kilograms is gently pushed off the edge of the tabletop. It's 5 meters above the floor. All right. Find the speed of the ball as it strikes the floor. Now, you might be tempted to delve into UAM. No need for any of that. No need at all. All we need to do is analyze the energy in the system. Look at what we start with. We have a ball that is ever so gently nudged off of a tabletop. So if we call that our zero line, then we can show the change in gravitational potential energy and set that equal to kinetic energy. Solve for velocity or speed that instant before it hits, because once it hits the ground, it's another problem. It's an impulse momentum problem. So let's look at plugging in some numbers here. And as you can see, does the mass of this ball matter? No, it doesn't matter. Mass is on both sides of the equation. We can cancel that out. No problems at all. And we know the acceleration due to gravity. We know the height of the table. This is very straightforward. Solving for the velocity, 10 meters per second. That is the speed of the ball the instant before it strikes the floor. What an easy approach compared to using UAM. Question 18. An archer pulls an arrow of mass 0.1 kilograms attached to a bowstring back 30 centimeters. You might want to be converting that, but we're going to just, I'm thinking out loud here, obviously, by exerting a force that increases uniformly. I'm going to underline that. A force that increases uniformly from 0 to 200 newtons. How much work does the archer do in pulling back the bowstring? So even though you're not given a graph, I've done a little college board sketch here to help conceptualize the problem. So this force is increasing over time. What I'm going to show you is what most students do in this situation. And it exemplifies something I spoke about on earlier problems with plug and chug using the work equation. So if you look at the area under this, all right, what does that give you? Gives you the, well, Force times distance. That's newtons meters. That's joules. The area under this is going to give us the work. Writing down what we know and looking at what most students do, which is wrong. This is incorrect, and let me explain why. We cannot put in 200 newtons. If the average force was 200 newtons, sure, but it's not. This force is increasing over time. It's changing. Look, it has a positive slope. It is changing over time. It is increasing over time. You cannot plug this into the work formula, and that's what I was getting at in earlier questions for this unit. Be careful using the work formula and just plugging it in. In this case here, it does not work. In this case here, because the force varies from 0 to 200, we cannot use this approach. However, what we can do is find the area under this graph and acknowledge that the area under this graph is equal to the energy. Okay? So force is not 200. Let's look at getting this one solved and figured out here. So we have the area under, which is this triangle here. So work is equal to 1/2 base times height, which is equal to 1/2 0.3 meters. Notice how I've gone ahead and changed that because the Newton is based on meters. And I have my force here. Now we can get the work that was done by the archer to pull back the bowstring equal to 30 joules or 30 Newton meters. Here's another way to solve this problem. We can actually find K. So what do we do with these graphs? We find slopes, we find area under. What is the significance of the slope? That's a Newton over a meter. Those are the units for the spring constant K. All right, so we can find K from this graph. I love this. So K is equal to, let's pick a point, 200 divided by 0.3 meters, because we don't want to use centimeters, and that gives us a spring constant of 667 newtons per meter. And now we can use the work is equal to 1/2 kx squared. All right, so when we plug in that information for the elastic potential energy, 1/2 kx squared, we now have K, we knew X, we get work is equal to 30 Newton meters or 30 joules. We get the same answer. Question 19. In the above question, the archer instead pulls back 60 centimeters, 0.6 meters. What will happen to the work done by the archer? All right, so here's what we're going to do here. So we have our K value. We found the spring constant at 667 newtons per meter. We talked in the previous question about the fact that the work was equal to that change in mechanical energy, in this case spring potential, which is 1/2 kx squared. We found K from the slope. We were given X, and we calculated 30 Newton meters. Good. So let's plug in the new values and the new information where that distance is doubled. So when that distance is doubled, we end up with 0.6 squared. We get 120 Newton meters. That's a substantial difference. So these are not directly proportional, linearly proportional. All right, and that should be obvious because that distance is squared. So instead of getting, say, 60 Newton meters, we have 120 Newton meters of work was done when the distance was doubled. If you were asked a conceptual question regarding a comparison between them, please consider making up numbers, putting them into the equation to help you conceptualize the problem. That is a semi-quantitative approach, using a combination of numbers and words to support or justify your response. All right, so in other words, 4 times the amount of work was done. We want to quantify that difference. We have our numbers, 30 joules versus 120 joules, so the distance doubled, but what happened to the work? It quadrupled. All right. Wow, let's go back to question 18 one last time. How fast is the arrow traveling when it is released? Okay, so we've gone through this a number of times, but if you're just picking up with question 20, we found that in 1830 joules of work was done. Okay, so work is equal to change in kinetic energy. Guys, this is a big thing on the AP exam, and you have to not forget work is equal to the change in kinetic energy. Well, initially the arrow has no kinetic energy. So kinetic energy final minus kinetic energy initial. Okay, so the total change is indeed 30 joules. So we can now set that equal to 1/2 mv squared. So our energy, our work is 30 joules, and we've just gone through the intuition behind that change in kinetic energy where there was no initial. So we're just going to set it equal to the kinetic energy, and this is kinetic energy final, and we're going to solve for velocity. All right, so when you do this, the velocity is equal to 24 meters per second. That is how fast the arrow is traveling when it is released. Okay. I need to, on occasion, reinforce an expectation that you'll look at units. It's always a great affirmation when you can look at units and you see that they work out correctly. You look at a derived unit of a Newton being a kilogram multiplied by the acceleration, or meters per second, multiplied by meter, because that's a Newton meter, but divided by kilograms. Okay, and taking the square root of that, we end up with the units for velocity. Good deal. All right, here we have a large ball of Play-Doh, and we're given the mass. I wonder if this is some of Sophia's Play-Doh. And Sophia has a catapult, and it's launched from the catapult with an initial speed of 5 meters and an initial height of 1 meter. Assuming level ground, what is the final speed right before the ball hits the ground? This we can solve using work energy theorem. This is the simplest way to solve this problem. So here's our ball of Play-Doh that flies through the air and smacks the ground. We're told the height is 1 meter, so we're going to be using universal gravitational potential energy. We're given the initial velocity, so there's motion, so we have an initial kinetic energy. All right, so what we can do to solve this problem is we can set our zero line, okay? And we'll set the zero line at the height the Play-Doh launches. That will allow us to compare these energies before and after. So we're saying, hey, this ball of Play-Doh doesn't have any gravitational potential energy initial because we set the zero line to be level with its initial launch. But it does gain gravitational potential energy, and the instant before it hits the ground, we can convert that into kinetic energy. So 1/2 mv squared. What do we have initially? Look at our mechanical energies. So we have kinetic energy initially. Sure, it's moving. Do we have any gravitational potential energy initially? Sure. We set our zero line right where it launched. And then what do we have in the end? Well, right before it smacks the ground, there's zero gravitational potential energy because all of that potential energy has been converted into kinetic energy. So it's all in the energy of motion. So what do we have after? We only have kinetic energy. Before, kinetic energy and gravitational potential energy. So mass cancels out. Sometimes, be careful with this, but mass cancels out. So we don't even need to carry that through. So it didn't matter that the mass of the Play-Doh was 40 grams. Algebraically, now we can plug in our values, our V naught, 5 meters per second, acceleration due to gravity. Our initial height can go into the gravitational potential energy. And what are we solving for? Final velocity. So the square root, when you solve through this algebraically, you're going to get that final velocity is equal to 6.7 meters per second. Again, we were able to set our zero line and think about where we set it. You have that ability to place that zero line where you would like to analyze energy. Okay, so in this case here, we wanted to set it level to the launch so we could convert that into final kinetic energy. Question 22. Given the force versus displacement graph shown to the right, for a net force applied horizontally to an object of 2 kilograms, which is initially at rest on a frictionless surface. Wow. Okay. Determine the object's speed at 2 meters. All right. So let's look at what we're going to need to do here. Where work is equal to change in kinetic energy, which is equal to kinetic energy final minus kinetic energy initial. When we look here at, and that was 2 meters multiplied by 20 newtons, okay? So, and we've gone through this. What do we do with these graphs? Well, if we find the area under, we're getting Newton meters, we're getting the work done. If it were, in other instances, if we had a spring, then we would be finding the spring constant by using the slope. In this case, that's not relevant, but those are the questions I want you to ask yourself every time you see one of these graphs. So in this case here, heck, we have a triangle. So we're going to multiply 1/2 times 2 times 20. Therefore, the work done is 20 joules, which is equal to the change in kinetic energy, which is equal to kinetic energy final minus initial, in this case 1/2 mv squared final minus 1/2 mv squared initial. So what do we have initially for this object? Nothing. Why? Because it is initially at rest. So what is this telling us? That's telling us Ki initial equals, there is none. So we're only concerned with the final kinetic energy, and we acknowledge that the work, which is the area under, is the change in kinetic energy, which means we can solve for velocity final is equal to 4.47 meters per second. All right, question 23. This diagram shows a toy car that has 16 joules of kinetic energy. It's on a frictionless horizontal surface, and it's heading toward a horizontal spring. If the cart moves to, if the cart comes to a rest after compressing the spring, 1 meter. What is the spring constant? All right, so it's going to compress at 1 meter. This is a pretty darn big toy cart, okay? So it's compressing a spring 1 meter. What is the spring constant? Let's look at how we're going to solve this to find the spring constant to be 32 newtons divided by meters, which is the answer. So, first things first, let's look at our kinetic energy initially. All right, so we're told that this cart possesses 16 joules of kinetic energy. So that is the amount of energy initially. All right, and what do we have after this scenario? Well, all of the kinetic energy is converted into spring. So in class, you'll hear me say, initially, is the cart moving? Is the object moving? Yes, so that it has kinetic. Has it done any interaction with the spring initially? No, it hasn't actually. Is gravitational potential energy relevant? No, it's not. So we only have kinetic energy. Now, afterwards, is there a spring? Yes, there is. Gravitational potential energy? No. The cart is at rest. So is it moving? No. So we end up with, essentially, we're going to set kinetic energy, or 16 joules, equal to the spring potential energy, or the elastic potential energy. 16 joules equals 1/2 kx squared. And rearranging this, solving for k, we get a final answer of 32 newtons per meter. And as I've said repeatedly, looking at units as a further affirmation that we've done this correct, they work out to newtons per meter as well. Question 24. A car initially traveling 30 meters per second slows uniformly as it skids to a stop after the brakes are applied. Sketch a graph showing the relationship between the kinetic energy as it's being brought to a stop and the work done by friction. All right, so if we stop and think about what's happening here, the car has kinetic energy. Negative work is being done by friction, and that negative work is slowing the vehicle. So we will end up with a constant negative slope that compares the kinetic energy as a function of the work done by friction, which means the vehicle is slowing as friction is applied to the system. In other words, kinetic energy is decreasing at that exact same rate. Question 25. A 2-kilogram block starts at rest and slides down a ramp from a height of 3 meters. Let's look at a schematic here. It reaches the ground with the kinetic energy of 50 joules. Determine the total work done by friction on the block as it slides down. Also explain what happened to some of the gravitational potential energy as a result. Let's look at the work that is being done. Remember, work is not kinetic energy, but change in kinetic energy. So our kinetic energy final minus our kinetic energy initial. What do we have out as far as our total mechanical energy? Well, we have gravitational potential energy at the beginning here. So if we look at those values, we can calculate the mechanical energy initial, which is the gravitational potential energy, to be 60 joules. However, we're told that this block reaches the ground with 50 joules of kinetic energy. So clearly, those do not equate. So the question becomes, what happened to the other 10 joules? Well, because we're showing here that the mechanical energy is now equal to the final. Well, what do we have on the final? Now we only have 50 joules plus the work done by a non-conservative force. So when we subtract that work from both sides, we can see how we're ending up now with only 50 joules at the bottom, because 10 joules must have been transformed or dissipated into heat and sound energy, non-conservative energies. A box is pushed 30 meters across a horizontal floor by a constant horizontal force. The kinetic energy increases by 300 joules. How much internal energy is produced? I.e., what are the non-conservative forces at work here? And how much energy was dissipated to those non-conservative forces? So let's look at a schematic here. We have a force applied to the right. Our displacement is to the right. So we can look at summing forces and also look at just simply our work equation being force distance cosine theta, where theta is 0 degrees and therefore equal to 1. We have our force applied of 25 newtons in that direction and a displacement of 30 meters. We get 750 joules of energy. However, we are told that the kinetic energy as a result only increases by 300 joules. Therefore, we know that the work done by a non-conservative force, i.e. friction, must have been 450 joules. That's how many joules were dissipated and transformed into heat, sound, deformation of microscopic particles, etc. Okay, so internal energy is another expression, another way of asking work done by a non-conservative force. I want to make sure you know that, because you will see this on the next exam. Internal energy, those are the energies that are dissipated by sound and friction, etc. Okay, all right, this looks like fun. We have ourselves an Atwood machine, a modified Atwood machine, and it is on a frictionless surface. And we are asked what happens to the gravitational potential energy and the kinetic energy of mass 1 and mass 2 when mass 2 is released from rest and the system accelerates. So if you think about it, if we look at, say, our zero lines for each mass respectively, you can tell mass 1 is going to stay at that same line and therefore will not experience a change in gravitational potential energy. However, it is going to be accelerated to the left, which means that it will increase in kinetic energy. Mass 2, however, will go down toward Earth, so its gravitational potential energy will decrease, and its kinetic energy will also increase because it is now accelerating downward. Question 28. A box of mass m is attached to a spring with a spring constant k. It's on a frictionless horizontal surface. It is compressed a distance x from equilibrium and released. Derive an equation for the speed of the box when the spring returns to equilibrium position. So let's look at our energies that we have here. So initially we're going to have a spring that is compressed. That's where we start. So our mechanical energy initially is going to be elastic potential energy or spring potential energy, 1/2 kx squared. Then it's saying derive for the speed. Well, once the spring returns to equilibrium, all of that potential energy has now been converted into kinetic energy, or 1/2 mv squared. So essentially what we're doing here is we have our information. We're simply going to algebraically rearrange this to solve for velocity, and that is our derived expression. And as you can see, whether we bring out the x or leave it under, this is our correct answer here. Question 29. Sophia accidentally drops her 1.5 kilogram dolly down a large slide at the park. This is a big slide, my goodness, because it rises 6 meters above the ground. Better be careful, Sophia. And Dolly slides down the slide, while 3 joules of negative work from friction are exerted upon poor Dolly. Once Dolly reaches the bottom of the slide, she flies off horizontally from 1 meter above the ground. How far from the base of the slide does Dolly land? All right, this one's going to be fun because we're going to use a combination, a little bit of everything here. Let's start with our schematic of the slide, Sophia and Dolly. Okay, so getting sort of our bearings here, we can see we have our 6 meters. What is very important to notice is the launch of little Dolly occurs 1 meter above the ground. So her total change in height here will be 5 meters, not 6 meters. So what we need to do is find her speed at the base of the slide. That is her launch velocity. And because her launch velocity is completely in the X or horizontal direction, we can use this information along with the range equation, and of course we'll find time of flight to determine how far little Dolly goes horizontally from the edge of the slide. So let's start with our energy argument here. We have our initial mechanical energies. That's going to be our gravitational potential energy. Remember, she launches off of this slide 1 meter above, so we need to be smart in where we pick our zero line. That energy is then converted into energy of motion, kinetic energy, along with work done by a non-conservative force. In other words, friction. And we are actually told that the work done on average was 3 joules. So if we look at our zero line and we set that where she launches, which makes sense in this case, as we've conceptualized at the beginning of this problem, her change in height is 5 meters prior to becoming a two-dimensional projectile. All right, so we have our initial and plugging and chugging, putting in this information, and the fact that we had 3 joules done by a non-conservative force, friction. We're going to subtract 3 joules from both sides, and we're going to then algebraically rearrange and solve for the velocity final. Okay, now velocity final of 9.8 meters per second now becomes the launch velocity in part 2. Now think about it, because Dolly launches from the horizontal. Dolly's initial velocity vertically is 0. So V naught in the Y is 0. Also recall V in the X is constant because there is no acceleration horizontally. The only acceleration once poor little Dolly leaves the slide is the acceleration due to gravity. Okay, so breaking this up now, we can look at finding time of flight. We always go for the time of flight in a two-dimensional projectile motion problem. And remember, the time is the same for the horizontal component and the vertical component. So you will always look at the time of flight first and foremost before moving on to solve for the horizontal displacement. So we get a time of flight equal to 0.45 seconds. Now we can move on and use our range equation for the horizontal displacement is equal to the velocity multiplied by time. We have the velocity that we found using work energy theorem. We can put that in there, multiply it by time, and little Dolly is going to land 4.4 meters from the base of the slide. Wow, this sounds like quite the slide. In question 30, we have a bungee jumper of mass 60 kilograms jumps or steps off of a 40-meter high cliff. It takes about 40 newtons to stretch the cord 1 meter. How close does the jumper get to the ground? Another beautiful drawing here showing our bungee jumper and the cliff. So the bungee jumper does not reach the ground, but we want to know how far did the cord stretch. So we're looking at the elastic potential energy in the bungee cord. We're also looking at gravitational potential energy, mg delta h. So there's a couple ways we can solve this problem. Write down what we know, and we need to find K. K is pretty darn easy to find in this case because it's 40 newtons stretches the cord 1 meter. So by definition, 40 over 1 is 40. Newtons per meter is our K, our spring constant. Now let's look at the energies at work here. So what we can do, there's two ways. As always, use the way that works best for you, the way that you understand. So the first way is to acknowledge that, okay, this guy is 40 meters high. Hopefully, the cord doesn't stretch 40 meters. That would be really bad. So the cord will stretch some distance, x. Okay, and that x is going to be the displacement of the bungee cord. Typically, we look at springs and anything with this elastic potential energy. So the distance that the bungee cord stretches is x, okay? So if we then say, all right, if that's the case, then the height that will be the change in height in the gravitational potential energy is also x, all right? So we put in x instead of mgh, we acknowledge that the jumper isn't going to go any further than x as far as our gravitational potential energy, so we can actually say change of h is equal to x. Now, if we put that information in, then we have an expression we can solve for and rearrange. We find x to be 30 meters. Now, recall the question's asking how close does the jumper get to the ground, so that would be 40 minus 30, which is 10 meters above the ground. Okay? Method number 2 is looking at energy before and energy after. So energies before, we have gravitational potential energy. We have that full height above the ground, above the earth of 40 meters. What do we have for our mechanical energies final? Well, we're still going to have some gravitational potential energy, but we're also obviously going to have quite a bit of spring potential energy. So you can see how we have the method 2 set up, and then the next steps are going to be to place into our gravitational potential energy final. We need to say, okay, what is the final height going to be? Well, it's going to be the initial of 40 meters minus some distance x. And that some distance x is the same distance that the bungee cord will extend. Okay, so this is a different way of setting up the problem, but what you can see is we're going to get the exact same answer. So just to recap, method 1, we went through the intuition and said, well, that change of height from gravitational potential energy standpoint is going to be the same as the distance that the cord extends. So let's just call h x. Method 2, we went from a pure energy, initial energy final, where in method 2, we said, well, this is our zero line. Okay, this is the zero line in method 2. And so clearly we're going to have some gravitational potential energy left over. The question is how much? And then we go through and say, okay, well, the height minus the distance of the bungee cord when it's fully extended is going to be that amount left over, okay? And X is going to equal, once again, exactly 30 meters, therefore 10 meters above the ground. Question 31. A boulder is dropped off of a 50-meter high cliff. On the way down, air resistance has an average drag force of 100 newtons on the boulder. Find the speed at which the object crashes into the ground. All right, here we go. We have our cliff, and we have our boulder, and we have a free body diagram. And in this instance, when we are not neglecting air resistance, we have a force that is opposing the direction of motion of this projectile. And we have that being the force of air on the boulder. We also have the force of gravity, which is the force of the earth on the boulder. We have two forces here. So we can go through and conceptualize, okay, if we straight up did mgh equals 1/2 mv squared, solved for v, we're going to get some value. So we're going to predict that this value is going to be less than expected because we do have work being done by a non-conservative force, i.e. the force of air on the boulder. Okay, so what do we have initially? mg delta h, and that's going to equal our mechanical energies final, which would be kinetic energy and work done by a non-conservative force, which is the air resistance, okay? If we plug in information here, we'll get our value 20,000 joules equals 1/2 mv squared plus 5,000 joules. That's the amount of negative work essentially done by the air resistance. So then we're going to subtract 5,000 joules from both sides. So our 20,000 joules is going to now only be 15,000 joules. Rearranging a little bit further, solving for velocity, we get 27.4 meters per second for the speed at which the object crashes into the ground. Now, you know I can't resist to sum the forces. So if you gravitate more toward a summation of forces, this will also work. So let's sum the forces vertically and set those equal. We have mass gravity. In this case here, we're calling down positive, directions relative as long as we're consistent. So mass gravity minus the force of air resistance is equal to mass times the acceleration vertically. Therefore, when we put in our information here, because we know on average that drag force, and we know the weight of the object is 40 kilograms multiplied by 10 meters per second squared, we can put in that information, divide both sides by the mass, and we get the acceleration vertically is equal to 7.5 meters per second. Now we can delve further using some UAM, and we can look at the velocity final and the velocity initial, and we can put in our values, being that we have the final equals the initial. Okay, well, the initial is 0. Remember, the boulder is dropped, so its initial velocity is 0. We're trying to solve for the final velocity in the y direction, and so plugging in our new acceleration of 7.5 meters per second, which is less than, obviously, 9.8 meters per second, we can then solve for velocity final, and by golly, we get 24.7 meters per second. Question 32. A 2-kilogram object accelerates uniformly as a net force acts upon it. During the 5 seconds this force acts, the object changes velocity from 3 meters east to 7 meters west as shown below. Determine the net work done on the object. Draw velocity as a function of time graph and use this graph to determine the displacement of the object. All right, this is a good one here. So one thing that might stand out as you approach this problem is, okay, I have time. Why am I given time in this case? I have, the mass. So if we kind of write down what we know, all right, we actually know quite a bit. Now, what's interesting about this problem is it goes on and says determine the work. Otherwise, you might straight up go into UAM mode, all right? But it's asking for the work. So thinking about what work is, well, work is a force multiplied by the displacement of the object parallel to that force, okay, which is where the cosine theta comes in. Or, which I don't know if that really makes sense, okay? Because we don't know the distance at which this force acts. At least we're not given that, not that we couldn't find it. But also recall that work is equal to a change in kinetic energy. That's the key. Do not forget, work is equal to a change in kinetic energy. If you can get to that point, this problem becomes very simple because all you need to do is plug in your values. You already have the mass. You know some force acts on it. What is that force? Well, it really doesn't matter for the problem, but you know its velocity initial and final. That means we can solve using work energy theorem, where work is equal to the change in kinetic energy, or 1/2 mv squared final minus 1/2 mv squared initial. And just like that, we get the correct answer. The work is equal to 40 joules. Now, for those of you who don't necessarily go that route, you could have also used UAM. All right, now I did mention, there's more than one way. Arguably, work energy is simpler in this case, but both will work out. So if we go in and take a UAM approach and watch your signage, to the east positive, to the west negative, we have our final velocity being -7, our initial positive 3 meters per second, plus the acceleration and the duration of that acceleration, which is 5 seconds. So we're going to need to find acceleration and then use Newton's second law to find the force and some other things here. So let's look at that. The acceleration is -2 meters per second. Now we can grab another UAM equation and find the distance at which that force acts. Now this problem is asking you to ultimately determine this from a graph, and we will do that. But using UAM, we can also confirm. So -10 meters is the distance that this force will act parallel to the displacement, okay? And so with that information, then we can use work. We can use the fact that the force is equal to mass times our newly found acceleration multiplied by our newly found change in position of -10 meters. And when we solve this, we get 40 joules. Now let's look at this graph we've been asked to do, okay? Think about what is happening here. This object is moving to the right and then changes direction and moves to the left, which is backwards. So think about what this graph will look like first and foremost. So laying it all out here, including our increments on our x and y axes, we're going to have something like this. We have our V naught indicated on the positive y-axis at 3. We then cross the positive x-axis entering into quadrant 4 on the Cartesian plane, which means the object's moving backwards, which means it stopped at an instant. Did the acceleration go to 0? No. The acceleration was constant as indicated by a constant negative slope. All right, let's finish this problem. So you're asked to find the change in position. We already found it using kinematic equations, but we're going to now find it using the area under the graph. So before we do that, you know I can't resist a little more UAM because I want to know where exactly does the object stop? I want to know where exactly do I cross here, because this was just sketched in. And according to what I've sketched in, you know, it's somewhere between 1 and 2 seconds where I am indicating the object stopped and changed direction, although the constant acceleration was always there. And so using UAM, solving for t, acknowledging that I'm trying to find velocity equals 0, I get 1.5 seconds. So now if I were to go back in, I could resketch this indicating it would cross here, which would make my slope just a little bit steeper than it is here. Let's find the area under. I see 2 triangles there. Notice when I am in this quadrant here, notice here the area under is actually the area above, okay? And I have the signage. You must be aware of the signage here as well. And when I add up these 2 triangles, I get negative 10 meters, which is exactly what we got using kinematics and UAM. All right, video analysis time. This is a trampoline, and this is found on PedersenScience.com, and we're going to answer parts A through D on this particular video. So, part A, what is the girl's potential energy when she is just about to leave the trampoline in reference to the ground? So this entire problem, the ground, the earth, is our 0 line. So everything we're doing is that change in height is referring to the distance above the ground. Okay, so what is her potential energy when she is just about to leave the trampoline? Here is a screenshot that is showing here right where she appears to be level with the trampoline. All right. And so according to this, if we have 1 here, we have 0.5, 0.6, 0.7, right around in there. And so looking at the gravitational potential energy, we can say, all right, her energy, her total potential energy at this point is mass multiplied by little g multiplied by the change in height, okay? And the change in height is relative to the Earth, which we have her at about 0.7 meters above the ground or the Earth. And so we get 381.5 joules being the girl's total potential energy. So in part B, what is the girl's potential energy when she reaches her maximum height? Okay, so we have this energy being converted into energy of motion, and then when that velocity reaches 0, she's at the top of her trajectory, and therefore we are have an increase in gravitational potential energy. So let's look at what that would look like. So here is about where I had her at the top. So this is a screenshot showing her, and you can see, you know, and everything was in reference to her feet here, 1.1, 1.2. So let's get our equation here. We have her now at 1.2, so everything else stayed the same, little g, her mass. So now we have a total gravitational potential energy of 654 joules. So where did that energy come from? That was from the trampoline. That was from elastic potential energy being converted into energy of motion and energy, gravitational potential energy. Let's look at C. Using these two potential energies from A and B, what is her velocity as she leaves the trampoline? So how fast is she moving upward the instant that elastic potential energy has been converted into kinetic energy? That's what C is asking. We have our initial energy plus the energy of kinetic energy initially, and we're saying that that is equal to her final gravitational potential energy. All right, so looking at our values here, our initial velocity, and we're subtracting out the initial gravitational potential energy. Remember, this problem could have been approached a bit differently had the problem not explicitly told you in reference to the ground, because you could have chosen a zero line for gravitational potential energy that worked and gave you the same answers, and perhaps you did that approach, and hopefully your answers are similar to what I'm getting here. So let's look at this. So we have a total change in mechanical energy of 272.5 joules, and that amount of energy is converted into kinetic energy. Solving for velocity initially, we get 3.2 meters per second. That's very reasonable for her velocity initially leaving the trampoline. Part D. Using this information and the fact that mechanical energy is conserved. So there's no energy dissipated. You're being told that. Calculate the spring constant K for the trampoline. All right. So we can do that pretty simply. We have our elastic potential energy 1/2 kx squared, and we know what that is. That's 272.5 joules. And we can measure our change in position of the trampoline, because it went from 0.7, 1, 2, 3, 4. It went up a total of 6 from where we started. All right. And now if we plug in that, and of course, if you have minor differences, that's fine. It's how you went about doing this problem that really matters. We get a spring constant of around 1,514 newtons per meter, ballpark. If you have answers anywhere in this area based on how we are, differences in how we perceive the video, that's no problem at all. Question 34, we have a roller coaster. It's at rest on point A. Now, this problem has been changed from your problem set, so make sure that these questions align with what you are using. Okay, so for part A, the car stops, it goes down a hill, it reaches B. Well, B is 10 meters above. I'm going to write that just so I don't forget. 10 meters, and this whole area here is equal to, from top to bottom, is 30 meters. Okay, and also we're being told C is 20 meters. So I'm just writing this information down so I don't make a mistake here further on. And then it goes up to C. C is 20 meters. Okay, A student assumes no energy is lost to non-conservative forces, sound, friction, air resistance, we're neglecting all of those, and solves for how fast the car should be moving at point C. Okay, using energy arguments. What answer did he get? Well, let's look at what's happening initially. We have gravitational potential energy, and what's happening in the final scenario at point C. Well, it depends on where we put our zero line, but essentially the overall change in height from A to C is only 10 meters. Okay, so let's look at our mechanical initial compared to our final. We have our initial gravitational potential energy, and we're saying we want to convert that into energy of motion, or the kinetic energy, 1/2 mv squared, and solve for velocity. And in this case here, we get 14.1 meters per second. All right, so look at how much energy was there initially and how much was there finally. Depending on where you put the zero line, you're going to get the same answer. B, the energy was dissipated as heat and sound. So B is saying if the final speed at C is actually measured with a sonar gun and found to only be 12 meters per second, what happened to the energy? Well, the student's assumption was inaccurate. This student neglected non-conservative forces. Well, there were non-conservative forces. There was negative work done on the roller coaster, and that resulted in a speed less than predicted if we neglected. So there was sound, there was heat, there was air resistance, there was a dissipation of these energies. Part C, how fast was the car moving at point C? Okay, how fast was the car moving at point C? All right, so if we go through and use this same argument here, and this should read B. All right, because we obviously already solved for C, 14.1. So how fast was the car moving at point B? That's going to be now a change in height, depending on where you put your zero line, but an overall change in height of now 20 meters as opposed to 10 meters when we solved part A for position C. So now putting in that information, we get a velocity of 20. Now, part D is asking you to compare 14.1 to 12, or excuse me, to 20. In other words, part D is saying if the change in height between A and B is 2 times that of A to C, why is the velocity not twice as fast? Now, this is a very common question, and you need to look at this and solve this semi-quantitatively. So let's look at what that looks like. We have our initial gravitational energies, and we're comparing that to the kinetic energy. Moreover, we're specifically comparing the height to the velocity. Notice that the height is proportional to the velocity squared. That's where the big change is. We're comparing height to a quantity that is squared. So they are not directly proportional. They are not directly linearly proportional. In other words, if h is 2 times, then we're going to get the square root of 2 for the velocity. So we would expect the velocity to increase. Yes, there is that positive correlation. All right, it's just not linear because of the square. So if we take 14.1 and we set and we multiply that by the square root of 2, shouldn't we get about 20? Indeed you do. 14.1 multiplied by that increase, the square root of 2, gives you a velocity of 20 meters per second. In question 35, this is your first power question. A mower pushes a large crate from inside a truck to the back, a mover, excuse me, which is a distance of 6 meters. The mover exerts a steady force of 20 newtons. If he moves the crate a distance in 20 seconds, so that's the big kicker here. You are given, clearly given information that will allow you to find work, but now you're given time, which means you can find the rate at which work is done. This is asking you what is his power output during this time. Work over time. Don't forget work is equal to force multiplied by a distance, cosine theta. And so you have force, you have distance, you have time. Plug and chug fest. Our power here is 90 joules per second. Question 36. Mary holds a 5-kilogram mirror against a wall. It is 1.5 meters above the ground, and she holds it for 20 seconds while little Johnny nails it in place. What is Mary's power output during this period of time? All right, let's look at a schematic here. I have the mirror. I have the change in vertical position being that it is at 1.5 meters. We have time, we have mass. So let's think about what's happening here. What's interesting is to go ahead and sum the forces here as well. So if we sum the forces, you can see here, and I'm doing this for a reason, not just because I love to sum the forces. You can see here, look at our force normal. Everything is flipped 90 degrees. So now force normal, which is always perpendicular to the surface, is coming straight out toward Mary. And we have a force of friction acting up the wall. And since the mirror is not moving, we're calling this the force of static friction, which now is equal in magnitude, opposite in direction of the weight of the mirror. All right, and of course, the a force applied that Mary's exerting on the mirror is to the right. Okay, so we have an object that's in what we call static equilibrium. So what is one of the qualifications for work? Well, there's this force exerted, and this force exerted leads to a displacement of an object, so it's going to move. And so there is no work done, and therefore their power is equal to 0 joules per second. Mary is doing no work, therefore there's no power that is being output during this period of time. Now, what's kind of interesting to think about is, if we look at the direction of these forces anyways, which maybe this is how you interpreted the problem, if the mirror did move, so if the mirror slipped, and whether it went up or down the wall, if the mirror did slip, so she decreased her force applied, which decreased force normal, which decreased the force of friction, and it converted it into kinetic friction now, so the object moves, heck, that force is still at a 90-degree angle to the slippage, okay? So still we would get cosine 90, which is 0 degrees, or 0 work anyways, which means 0 power. Question 37, we have a cyclist that develops 210 watts of power while pedaling at a constant velocity of 7 meters per second east. What average force is exerted eastward on the bicycle to maintain this constant speed? So, a little different here. We're asked average force. You are told constant velocity, but we're asked specifically about an average force that is exerted. And we're given power. So here's what you must remember. That especially on the AP exam, where you will encounter very few, if any, power questions, very rarely, but they have been known to be on the exam. you need to remember what is power. It's the rate at which work is done. What is work? Work is force multiplied by that distance, divided by time for power. What is distance over time? Well, that's going to give you the speed, okay? Change of position over time. That's going to give you the velocity. Let's look at this mathematically. It's also in the facts preceding these two questions. So here we look at change in position over change in time. What is that? That's velocity. So what is power? Power is actually the force multiplied by the velocity. Once you get to that point, you can easily solve for the force here. Given 210 watts of output, dividing both sides by 7, the average force exerted is 30 newtons east. All right, units, you know, it's always a further affirmation to look at your units. Joules divided by seconds, divided by meters over seconds. Units cancel out, leaving you with newtons. Here we have 5 stacks, and they each contain 3 blocks. The masses of the blocks are given in the diagram in terms of mass M. Each block has the same height, and the center of mass of the block is also the same. The blocks are on a flat surface, and you're being asked to derive equations in terms of M, G, and H that will allow you to rank from greatest to least the amount of work required to assemble the blocks. Let's think about what's happening here. The lowest block, all of mass M, you're not going to move that one. So you're lifting the other blocks a height of M, and you're lifting the top block a height that is double, okay? So if each has the same height, H, then if you look at the 5, and this is being lifted, so a force is applied upward, all right? And that force is resulting in an upward change in vertical position. Work is done. Again, each one of these has the same height. You're not moving this low block. So if this 5 mass block is 5 mass, it's lifted a height of H, and G is constant for all. This top block here is lifted a height of 1H, 2H. So let's look at the mathematics here. Force equals mass times gravity. That's the weight. The X is going to be the height, cosine 0, 1, because the force results in a displacement that is in that same direction, and I've gone over that. So what we need to do now is go ahead and move on with our derivations for A through E. For A, we have, what do we have initially? Okay, how much is being done here? We have this 5 multiplied by G multiplied by H. And we're adding, because we're going to do, now we're going to add this top mass here, which is mass M multiplied by G multiplied not by H, but by 2H, because it is lifted twice the height. Okay? And so that gives us an answer of 7 multiplied by mass, gravity, height. I'm going to do the same for B. And we get the 3M lifted a height of 1H. See, each one of these is H, right? And remember, the bottom block, you're not moving. All right? And it's lifted a height of H. And then we have another 3 mass box, and it is lifted a height of H plus H. So its total height is all the way up here. That is 2H. Okay, so we're going to add that, and we get 9 mass gravity height. For C, Along those same lines of logic, 8 mass, gravity, height. D, you'll get 10 mass times gravity times height. And for E, you will get 11 mass, little g, h. Now you can rank. E is greater than D, is greater than B, is greater than C, is greater than A. And that's how you would approach this particular problem. But the whole problem was predicated on an understanding of the displacement of the object, the work being done to cause that particular displacement, and then simply finding a quantitative approach to actually rank them. In this case, they're all relative to the mass, gravity, height. Question 39. Rock A is dropped from the top of a cliff at the same instant an identical rock B is thrown horizontally away from the cliff. You are being asked first to draw some motion time graphs. But before we even begin that, we need to talk very briefly about rock A, rock B. Let's go ahead and revisit some of our facts for a two-dimensional projectile. So let's start with rock A. Rock A has an initial velocity vertically of 0. Rock A will have the same time of flight as rock B because they are dropped from the same height. Rock B has a greater overall velocity because it has a horizontal component. Both rocks will have the same acceleration, and that is the acceleration due to gravity. Rock B does not have any acceleration horizontally, and therefore rock B's horizontal velocity will remain constant throughout. However, for rock B, when we take those vectors and add them up orthogonally and use the Pythagorean theorem, we see that rock B has an overall greater velocity upon impact. Now let's look at our motion time graphs, and let's start with rock A. Rock A has, based on the information we're given with the origin, is moving backwards or moving into quadrant 4 on the graph and has a slope of a -10. Okay, so a slope of -10. And we have this information. If we take the slope, which is -10 and constant, then we get our acceleration as a function of time, which is -10 and constant throughout. Let's talk about rock B. Rock B's, well, let's first talk about its X and its Y direction. Let's look at what it would look like in the vertical. It looks identical to rock A as we conceptualized at the start of the problem. The reason it looks identical is because it's the same acceleration, and that is the acceleration due to gravity. So we get the same graph, we get the same slope of -10. Now, if we look at the horizontal component of the velocity, it is some constant value. The slope is 0, which says there's no change in velocity over change in time, i.e. there's no acceleration, and we know that. But we're also told that away from the cliff is the positive direction, and this rock has a displacement that is away from the cliff, so we're going to call that a positive constant velocity of some value. And of course, the only acceleration, which is in the same for both of these, which is why the time of flight would be the same given the height is the same, is the acceleration due to gravity of -10 meters per second. Part B is the kinetic energy, 1/2 mv squared, of rock A at the start of motion, greater than, less than, or the same as rock B. Well, rock A has less initial kinetic energy because rock A has 0 initial velocity. It is dropped. Whereas rock B has an initial velocity in the x direction. So that means that rock B is going to have a greater overall kinetic energy because it has a greater overall velocity. In C, you're asked about the kinetic energy halfway down, okay? So along those same lines of argument, we can say, well, rock A has less. Rock A does not have that x component, all right? And as I mentioned earlier, if we add the vectors orthogonally for the rock B and use the Pythagorean theorem, we can see that the overall, that hypotenuse, the velocity of rock B is going to be greater than rock A because it has a horizontal component. And because the velocity is greater for B, 1/2 mv squared, the kinetic energy will also be larger for B. Question 40. A 100 Newton box is initially moving upward. So V naught vertical has some positive value, and we're told it's moving at 4 meters per second. A woman is applying a vertical force of 80 newtons. All right, think about it, guys. The weight of the object's 100 newtons. The force applied is 80 newtons, which is less than 100 newtons. So even though there is an initial vertical velocity of 4 meters per second, this object is slowing. Sketch a graph of the velocity and the kinetic energy of the box as a function of time for 2 seconds. Let's sum the forces on this. And as you can see, the weight, mass gravity, so this is a 10 kilogram object, is shown to be slightly greater in magnitude than the upward force applied. So the mass times gravity, or the weight, is greater than the force applied. If we go one step further and sum these forces vertically, we get that 80 newtons minus 100 newtons is equal to 10 kilograms multiplied by the acceleration vertically. All right? So if we even go one step further, we can solve for the acceleration vertically. It is equal to -2 meters per second per second. All right? And that should make sense, which means that this box will eventually stop. All right, so let's get to these motion time graphs. Let's start with our velocity as a function of time. We have V naught, so that is indicated on the graph. Its V naught is 4 meters per second. We have, over the course of 2 seconds, which is actually when the box stops. Think about it. It's moving 4 meters per second, and the acceleration is -2 meters per second per second. So that first second, it slows to 2. The second, it slows to 0. So at t equals 2 seconds, we have this object at the positive x-axis. So, part 2, kinetic energy as a function of time. So for part 2 here, we're going to need to compare velocity to the kinetic energy. Kinetic energy is proportional to the velocity squared. Think about it. The overall kinetic energy in joules when compared to the velocity squared. So from a mathematical reasoning standpoint, the kinetic energy is proportional to the velocity squared. Or velocity is proportional to the square root of the kinetic energy. This will not be a straight line. That's what I'm getting at. This will be quadratic. And it should make sense that this kinetic energy, that the velocity that the kinetic energy is decreasing quadratically. Okay, so it's decreasing, but it's at a rate that is proportional to the velocity squared. That is a key piece to make sure you pick up on moving forward. In question 41, we have our first pendulum of the course, and we're told a mass m and it has a light string of length L. So we're going to be deriving an expression is what this boils down to, and it's released at rest from an angle of phi, okay, as shown. So derive an expression for the maximum speed of the pendulum as a function of phi, length, and any other required fundamental constants like little g and any other constants that may come into play for any derivations you approach throughout this course. So first things first, here's our pendulum, and this pendulum has been displaced through an angle phi, and so it is released from a greater height than it was initially. And then when you let go of the pendulum, it's going to swing. It's going to get faster and faster and faster as gravitational potential energy is converted into kinetic energy. It's going to be moving the fastest when it gets back to equilibrium. Looking at our initial versus our final mechanical energies, initially we have all gravitational potential energy. Looking at the conversion of the energy as it passes back through equilibrium, it's all the potential gravitational energy is being converted into the energy of motion. So this pendulum is moving the fastest when it gets back to this area right here. Okay, it's moving the fastest. That's the intuition to start this problem. We have a classic scenario where all of our potential energy is being converted into kinetic energy here. And we're going to solve for V in our derivation. All right, I broke this into some sections here. So I have section 2 being this big red section here. And as you can hopefully see, that is the height, that the change in height for the pendulum. So this pendulum has been pulled back to this height and therefore has a displacement of an angle phi. Okay, now segment 2 is going to also be critical. And then the overall length of the string is L. So this overall length all the way down, 1 plus 2 is L. All right, and then as it's pulled back to here, we get this delta H that's going to be what we derive and put into our energy equation above here. So let's go ahead and look at segment 1. Segment 1 is L cosine phi. L cosine. Now ignore this, ignore the red piece down here. Let's just look at this triangle here. Let's look at our 90-degree angle right here, and our angle, our hypotenuse, and we know adjacent over hypotenuse, so segment 1 is our adjacent, L is the hypotenuse. So rearranging this for this adjacent side, we get that the adjacent side, which we've labeled 1, is L cosine phi. Next step. L, recall, is equal to these two segments put together, 1 plus 2. All right, so that means that L minus segment 1, okay, if we subtract this segment here from L, we're left with H, which is what we're trying to get. So segment 2, which is h, is equal to the length of the string minus segment 1, which we have determined is length multiplied by cosine of the angle phi. Okay? Are you with me so far? So, if we take this information here, we have L minus L cosine theta is the height. L minus segment 1. Segment 1, using the trigonometry, is L cosine theta. If we subtract that from L, we get the height. If we factor out the length, which you can do, clean this up a little bit, we get that the height is equal to the length of the string multiplied by 1 minus cosine phi. That is the height. Now, I've taken an exceptional amount of time to explain this to you. The reason why is this relationship comes up in about 3 more units. So this is very important for you to make sure you conceptualize, make sure you understand. And if you're not following what's going on, come to class and we will set up a simple pendulum and I will show it to you. But now that we know the delta H, or the height of the pendulum, we're ready to derive our final equation, which means we're going to take everything in our energy equation and we're going to substitute in any values and simplify. For example, as shown in yellow, we now have a derivation for the height of the pendulum. So we're going to take that and we're going to plug it into our expression and algebraically solve for velocity. So mass cancels out. Remember, in your derivations, you want to ultimately simplify it as much as possible. So plugging in our derived height based on these quantities for the pendulum, canceling out mass, algebraically solving, we get the velocity is equal to the square root of 2 multiplied by little g, which is one of our required fundamental constants, multiplied by the length, and then ultimately multiplied by the quantity 1 minus cosine phi. And that is our derived expression for the speed of the pendulum as it swings back through equilibrium. Remember that because all of the potential energy is converted into energy of motion at that instant, that spring, or excuse me, that pendulum is moving the fastest as it swings back through equilibrium. So we have actually derived an expression for the velocity maximum for a plumb bob on a pendulum as it swings back through equilibrium. And I'll see you guys in class.